let's continue to conservative and non-conservative forces. Okay, now we are going to learn about another type of energy that can a system possess or store. Okay, which is the internal energy. Okay, so let's observe this system. Right, we have a textbook, physics textbook. Okay, is a given a force, okay, that causing the textbook, okay, slightly to the right, okay, until it reach X final position here. So means that this textbook was pushed by external agent or our hand, let's say, from this side, and is going to move to the right. Initially it has V initial, and eventually this textbook going to stop, whereby finally the V is 0. Okay, who is the one that going to cause the textbook now slow down and finally stop? Which is frictional force, kinetic frictional force. Okay, due to the rough surface, okay, experience between the physics textbook and also the floor. Right. So now let's consider the surface here as the system, right? Vice versa of the usual that we used to. So now we are going to consider this surface as a system, right? So from our discussion of work, okay, we can argue that the friction force from the sliding, okay, book, okay, does work on the surface as well. So this is the one that experienced by the book. How about the one that experienced by the floor or the surface? Okay, it must be action reaction, remember? So there is a frictional force as well experienced by the surface. The blue color here experienced by the surface. It must be same magnitude, opposite in direction. Action reaction force. Right. The friction force on the surface is to the right, as I draw now. Okay, because the book moved to the right. Right. So the work done on the surface is therefore, okay, positive. Okay, the work done on the surface. Okay, so remember we are considering the surface as the system, that we are focused on the surface. So the work done on the surface will be positive because the FK experienced by E is to the right, the displacement also to the right. But, okay, the surface is not moving after the book has stopped, isn't it? Okay, positive work has been done on the surface. Yes, we know that. Okay, but there is no increment in the surface kinetic energy. We cannot observe any V, okay, for the surface. The surface is not moving, right? There is no changes in the potential energy of the surface as well. Okay, we don't observe that the surface is getting a level up or higher in position. Okay, so we know that work has been done. Okay, but what is the energy? Okay, so from our everyday experience, okay, sliding over surface with friction like this, okay, we can guess that the surface will be warmer, isn't it? Alright. Okay, this is actually the work done, okay, on the surface has gone into warming the surface rather than increasing its speed or changing the configuration of a system, not higher up or level down in terms of position along x-axis or vertical. Okay, we call the energy associated with the temperature, increment of the temperature just now, okay, as its internal energy. Okay, symbolized as E internal. Right, so the work done on the surface just now is equivalent to E internal. Okay, Now let's consider the book and the surface in this diagram. Right? We are going to consider both. Right? As a system. After the book is released, while it is slowing down, no work is done on this system. Okay, initially, the system has kinetic energy because the book is moving with V initial, right? Okay. While the book is sliding, the internal energy of the system is increases. Okay. Initially, okay, kinetic energy. Okay, no yet internal energy. But as the book is moving, it's slowing down, kinetic energy become less. Okay, converted into internal energy. Internal energy become higher or bigger. And finally, eventually, when the book already stop, okay, what will happen in terms of kinetic energy is zero, right? In terms of internal energy, it's reaching maximum, which is equivalent to the total energy. Total energy remain the same throughout, okay, the situations given. We can consider that the friction force within the system, that is between the book and the surface, as a transformation mechanism for energy, right? Okay, this force transform the kinetic energy of the system into its internal energy of the system. This is also similar situation when you rub your hand together briskly to experience this effect. Okay, warmer, isn't it? Alright. As I mentioned in the previous slide just now, okay, the E internal is actually work done by the friction force. Okay, so what is friction force? Okay, friction force is actually a kind of non-conservative force, right? So when we have non-conservative force, we must have also a pair of it is the conservative force. So what are the conservative and non-conservative forces? Alright, so depends. Let's take a look on this diagram. Okay, this setup. We have a block, okay, on the upper part of the ramp, right? And the ramp is rough surface, right? So let's say now the block going to move from upper part of the ramp until the end of the ramp, right? So we have two kind of forces involved here. Firstly, frictional force, right? And then also weight or gravity. We do have a normal, but then normal has no work done, okay, because normal is perpendicular to the displacement taken by the block. So work done by normal is equivalent to 0 because it's equivalent to W normal is equivalent to N L, the length of the ramp, let's say, cos 90. So it becomes 0, right? We have friction and also friction, okay, is output like this, kinetic, and we also have weight. Alright, so the difference between these two kind of forces, okay, is actually on the path taken. Okay, how to evaluate conservative and non-conservative. What does that mean by conservative? Conservative means it's not depending on the current situation. It's only refer to initial and final position. Okay, it's not depending on the way or path taken. Okay, but for non-conservative forces, the work done by the non-conservative forces, which is our friction just now, okay, is depending on the path taken. Okay, so let me elaborate more. Right, work done by the weight. Let's say this object is having displacement along this path 1, or we can imagine that we take away this ramp and the block is moving downward, falling down, taking a path number 2. Or the block is moving by taking path number 3, falling down in this pattern. Okay, regardless whether pattern number 1, path number 1, path number 2 or number 3, okay, the y initial and the y final or delta y is the same. So work done, okay, due to the weight, okay, will be the same. Doesn't matter which path taken by the block or the object. But, okay, if we consider work done by the friction force, okay, take a look. Let's say this is top view. We have top view, okay, of the block on the ramp. Okay, this is on top view. Okay, so we have this kind of visualization. So this is our block. Let's say our block is placed, okay, from its initial position up to final position here by taking path number 1 straight, or by taking path number 2, or by taking path number 3. Okay, for sure, amount of work done. Okay, imagine you are pushing this block in 3 different paths here. The amount of work being done, okay, on the block by the friction force are different. It's depending on the path taken by the block. So this kind of force, whenever the work done by it, okay, is depending on the path taken, is known as non-conservative force. So it's depending on the path taken. So we can conclude that work done by a conservative force on a particle moving between any 2 points is independent of the path taken by the particle. Work done by the conservative force on a particle moving through any closed path, okay, is 0. Okay, what does that mean? For this one, what does that mean? The block is moved from this y initial, okay, travel and finally reach this position, okay, which is the y final. Okay, your delta y will be 0, isn't it? That is the meaning closed path. Okay, initial point and final point is the same, right? For example, gravitational force, electric force, elastic force within a spring, also a kind of conservative forces. So let's take a look on the formula or calculation of work done by the gravity or weight just now. It's equivalent to downward, right? Negative mg in terms of j dot, by definition of work done is dot product, right? The delta y, y final minus y initial, j as well. So j dot j become 1. So what we have here, mgy initial minus mgy final, right? And about the elastic force that we've learned before, okay, work done by the spring is equivalent to half kx initial square minus half kx final square. Non-conservative force, right? For the non-conservative force is this situation just now, right? This is for the situation of the conservative force, work done by the weight. Okay, so within, okay, the non-conservative or conservative forces, both of it, okay, E mechanical is equivalent to kinetic plus potential. The graph that madam already showed to you just now. One of it like this, the other part of it like this. Still remember? This is E versus X. This is U, this is K. Right? So E mechanical within the system always a combination of kinetic and also potential energy. Work done by a non-conservative force on a particle moving between any 2 points is dependent on the path taken by the particle. Example, friction force, tension, normal, normal force, and force applied by a person, push or pull. This is in more complicated way. Motor or rocket propulsion, air resistant, because this one I know all this while you are learning that a push or pull as a constant force. In real, that is not a constant force, as you go further later on, because when we push or pull, the force begin from zero, right, until it reach certain amount. So it's not a constant actually. Goes the same to the tension. As of now you are learning that tension is a kind of constant force, right? So to mention here, actually is this not, right? And also air resistant. Air resistant also a kind of non-conservative force. Right, relationship between conservative forces and potential energy. We know just now W internal, work done internal, is equivalent to U initial minus U final, which is equivalent to negative of delta U. And W internal can be also calculated by using integrand of fx to the respect of x from initial up to final, which is going to be equivalent to this value, right? So if we rearrange, the negative is bring here, so you have this kind of, right? So it means that also can be written in terms of this, right? And finally we can say that fx is equivalent to negative du over dx. What does that mean? F along x is a function of, or depending on the change in potential energy to the respect with the position of the object, right? So energy diagrams and equilibrium of a system. The motion of a system can often be understood qualitatively through a graph of its potential energy versus the position of a member of the system. Right, consider the potential energy function for a block spring system here. Given U as half kx square. This function is plotted versus x, right, in this figure. Where x is the position of the block. When the block is placed at rest and the equilibrium position of the spring x equivalent to 0, where we know that Fs also 0, it will remain there unless some external force, right, F external, acts on it. If this external force stretch the spring from equilibrium position, which is x equivalent to 0 just now, to x, reaching x positive, and the slope of du dx is positive. Therefore, force Fs here, exerted by the spring is negative because it's to the left, and the block accelerate back toward the x equivalent to 0 when released. If the external force compress the spring, vice versa, the situation, the x going to be negative and the slope also going to be negative, right? Therefore, the Fs is positive because the Fs going to move or try to move to restore the block to x equivalent to 0, right? And again, the mass going to move towards the x equivalent to 0 upon release. From this analysis, we can conclude that the x equivalent to 0 position, for a block spring system like this, is one of stable equilibrium, right? There is any movement, stable equilibrium. What does that mean? Any movement away from this position results in a force directed back toward x equivalent to 0. Okay, that is the definition of this system having stable equilibrium. Regardless whether we apply force to the left, to the right, it's always going to be moved towards the x equivalent to 0. So x equivalent to 0 here known as stable equilibrium. Right. Okay, another type of equilibrium, we have unstable equilibrium. Okay, which going to be in opposite to the graph that we have just now, which is here. Okay, so the situation also going to be in opposite. All right, what does that mean? Okay, from this diagram, okay, in terms of graph here, fx equivalent to 0, all right, at x equivalent to 0. And so the particle in equilibrium at this instant, okay. This position, however, unstable equilibrium for following reason. Why? Suppose the particle is displaced to the right, x is bigger than 0. Because the slope is negative. Okay, so fx is equivalent to negative du over dx. Right. Okay, is positive and the particle accelerate away from x equivalent to 0. So the particle accelerate away. That is the meaning of the slope. If instead the particle is x equivalent to 0 now and displaced to the left where x is less than 0, okay, the force is negative because the slope is positive. Okay, so x is less than 0 and then the particle again accelerate away from the equilibrium position. So the x equivalent to 0 here, the equilibrium position here, is known as the unstable equilibrium. We have another one which is neutral equilibrium. Okay. Okay, what does that mean? Okay, this only arises when U is constant. Okay, potential energy is constant. Right? Over some region. Okay, small displacement of an object from a position in this region produce neither restoring or disrupting forces. Okay, for example, okay, a ball lying on a flat surface, right? Horizontal surface. Okay, this is example of the neutral, right, equilibrium. So that's it for this topic. Thank you very much for watching. Do not hesitate to ask any question regarding this lecture to me. That's all. Assalamualaikum warahmatullahi ta'ala wabarakatuh.